Hi. So in this video we're exploring related rates, which is again an extension of the implicit differentiation method. Okay? Today in this video we're going to look at a situation like this. Suppose that the price P in dollars and the weekly sales X in thousands of units of a certain commodity satisfy the demand equation 2 times P cubed plus X squared is equal to 4,500. Okay? What we're supposed to do is determine the rate at which sales are changing at a time when X is equal to 50, P is equal to 10, and the price is falling at the rate of $0.5 or 50 cents per week. Okay? There's a lot of different things that are happening here. As you can see, related rates, we're going to have to differentiate this with respect to time, because they want to know the rate at which sales are changing at a time. Okay? So sales over time. We're looking for the derivative of sales, or dx over dt. And t, remember, is the third variable with which both x and p are a function of. Okay? So the derivative of the sales with respect to time at a specific, with some specific conditions here. We're given that x is equal to 50, we're given that p is equal to 10, and the price is falling at the rate of 50 cents per week. Now, price from our word story problem here is our variable p. The price is falling per week, so that's, you can almost put that into price per week. So p dp over dt, okay? Our price is falling, so falling is going to have a negative slope. dp dt is actually equal to a negative 1/2. Okay? dp, that's a negative $0.50 per week. It's also nice to note that t is measured in this problem in weeks. Okay? What we want to do is evaluate our equation here. 2p cubed plus x squared is equal to 4,500. In a situation where we're trying to find the derivative of x with respect to t when x is equal to 50, p is equal to 10, and dp dt equals negative 1/2. So what we're looking for here is to find dx dt by itself. Okay? I'm going to keep all of these things in mind because we really want to make a statement at the end that it helps explain what is going on in our problem. So let's go to work and do the calculus first. Okay? So here we've got things in terms of p and x, but we want to take the derivative with respect to t. Okay? So the derivative with respect to t here, I'm going to take and just simply rewrite. Okay? We want dt of 2p cubed plus x squared equals 4,500. And here we have a sum rule on our one side of our equation. We've got a constant on the other. Let's go through and evaluate here. d dt of 2p cubed is going to be 6p squared times dp over dt plus the derivative with respect to t of x squared is going to be 2 times x times the derivative of x with respect to t. Okay? So that takes care of this side of our equation. Now to go to the other, this is all going to be equal to the derivative with respect to t of a constant number 4,500, which is simply 0. Okay? So that's great. There's our first step. What we're looking for is dx dt. Okay? We want to get this term right here all by itself. And so now I'm going to take and use algebra to move things to the other side so that I've got this isolated. Okay? First thing I'm going to do is subtract 6p squared dp dt quantity from both sides. Okay, this cancels out, leaving us with 2 times x dx dt is equal to a negative 6p squared dp over dt. Okay, and now we're just going to divide both sides by 2 times x. Okay, so this side cancels out, we get dx dt is equal to, well, this negative 6 halves is really just a negative 3, p squared, all divided by x, times the change in price with respect to t. So right now what we have is our desired derivative. We got a desired derivative in terms of p, x, and dB dt, and we actually know what those 3 are. We're going to evaluate when x is 50, when p is 10, and when dP dt is equal to a negative 1/2. So evaluating at these numeric values, I've got a negative 3 times p squared, or 10 squared, which is 100, all divided by x, which is 50, times dP dt, which is a negative 1/2. Okay, well, looking at this, I've got a negative 300 divided by 50, so that's a negative 6 times a negative 1/2 gives me a positive 3 being equal to dx over dt. Now that's nice and all, but what does this mean? Okay, what does this mean? Well, now we need to bring that back to the context of the question. Okay, again, the question, as I said, and if you want to look at this again, please take and rewind the video. But I'm going to erase this. To suppose that the price P in dollars and the weekly sales X in thousands of units of a certain commodity satisfy the demand equation given here. We're supposed to determine the rate at which sales are changing at a time when X is equal to 50, P is equal to 10, and the price is falling at the rate of 50 cents per week. What we need to say is how to relate this 3 of the derivative of x with respect to t, what it means. Okay? Now, if the first derivative is positive, if you go back to your graphing skills, first derivative being positive, that means that we are increasing. We're on the rise. Okay? So we can say that and what is x again? X is sales in thousands of units. The sales of the commodity are, here's an important one, is it's a positive 3, it's increasing, it's rising. Just choose the correct word for the context. Our sales are actually rising at a rate of, and now we need to make sure we interpret this 3 correctly, and it's 3, but x is in terms of thousands of units at a rate of 3,000 units per what time period? Again, per week. Okay, where time is weeks. So 3,000 units per week. Okay. This is what really matters after you go through your whole related rates. Being able to explain what you've got there.